Why does the universe make sense? It might sound like a strange question, but if you stop to think about it, why does everything follow rules at all? From the way light travels to the way stars burn, from the smallest atom to the grandest galaxy, the universe operates in a regular and repeatable way. We see patterns, constants, and laws. But why should reality have rules in the first place? Why shouldn't it just be completely random? We often take these laws for granted: gravity, motion, energy, as if they've simply always been there. But where did they come from? Why do they work the way they do, and could they have been different? Are they truly unbreakable? In everything we see, from a falling leaf to a swirling galaxy, there is a sense of order. Things behave with structure and consistency. We call these patterns the laws of nature, as if the universe is following a hidden script, a kind of grammar that shapes how everything unfolds. In language, grammar tells us how to build sentences and how meaning is shared. We rarely notice it, but without it, our words would be nothing but noise. In the same way, the universe follows an invisible set of rules that shape every event, from the motion of stars to the firing of neurons in our brains. Why isn't everything just pure chaos? Imagine a universe without reason, where an apple might float up today and fall down tomorrow, where atoms scatter at random and time moves backward without warning. In such a place, we could never understand or predict anything. It would be a universe without memory, meaning, or structure. But what we have is different. Certain actions always lead to certain results. Water freezes at a specific coldness, and planets follow predictable paths. One possible explanation is that we live in a kind of selection bias. In a universe without order, complexity could never arise. There would be no stable atoms, no stars, no chemistry, and certainly no life. So perhaps we find ourselves in an orderly universe simply because only such a universe could allow someone like us to exist and ask the question. While this doesn't explain why the laws exist, it suggests why we should expect to find some kind of structure. Yet, the mystery remains, because the universe is not just orderly, it is also beautiful and understandable. The laws of physics can often be written in elegant mathematical language, where the same rules that govern a falling object also explain how the moon orbits the Earth. The building blocks of the stars, the oceans, and our own bodies are the same, as if reality follows a deeply interconnected and carefully arranged design. While the grammar of a language comes from the mind, the grammar of the universe was there long before humans appeared. Who or what wrote these rules? Have they always existed, or did they blink into existence with the Big Bang like a cosmic operating system? Some thinkers suggest these laws are more like habits that the universe developed over time, paths that became worn and steady. Others believe they are eternal, existing outside of time as a code that the universe simply follows. Both ideas lead to more questions. If laws evolve, what governs that evolution? And if they were always there, why do they take this specific form instead of something else entirely? It is also a strange fact that the universe allows beings like us to understand its grammar. We are small creatures on a tiny planet, yet our minds can grasp concepts like relativity and quantum mechanics. The grammar of reality is not just consistent, it is legible, as if the universe is speaking a language we are capable of learning. This leads some to believe that the universe is deeply mathematical at its core, that reality is an unfolding equation, and every object is a piece of that formula. Math. The word law sounds final, but when scientists talk about the laws of physics, they don't mean absolute commands. These laws are summaries of countless observations, maps of the behavior we see. Newton's laws worked perfectly for centuries, but eventually, we found places where they no longer applied, especially at extreme speeds or at the very small scale of atoms. This gave rise to Einstein's relativity and the strange quantum world. It teaches us that what we call laws are actually models based on our observations. When our measurements get better, our laws often need to be revised. This doesn't mean the universe is changing, but rather that our map of its patterns is becoming more accurate. Imagine a world with no one to watch it, no humans, no animals, no conscious minds. Would gravity still exist? Would electrons still spin and stars still burn? Most of us believe they would, that these laws are part of the universe itself. But the truth is, we don't know what the laws look like without an observer, because we have never seen a universe without one. When we say light travels at a constant speed, we are describing what we measure. These are patterns that have never failed us so far, but that doesn't guarantee they never will. If the laws of nature aren't fixed but instead emerge from the universe's own history, then what we see today is just the current state of a changing system. Perhaps we are simply pattern-seeking animals, wired to find order in the noise. We see faces in clouds and shapes in the stars, so when we find structure in nature, are we discovering something deep, or are we projecting something familiar? We only have one tool, the human mind, and everything we see is filtered through it. In quantum physics, the act of measuring seems to affect the object itself, suggesting that reality might not be fully real until it is observed. If the mind that finds the pattern and the pattern itself are connected, then our version of reality is always shaped by the tools we use to describe it. Physicists call it one of the most mysterious numbers in all of nature, a value whose origin remains unknown, yet even a tiny adjustment to it could tear the entire universe apart. Many scientists have spent their lives searching for a deeper pattern to explain these constants, perhaps a single equation that ties every number together into a grand theory of everything. This is the dream of uniting gravity, quantum mechanics, and all the forces of nature into a single set of rules. If such a theory exists, it might finally tell us why these numbers are what they are, but so far, that ultimate explanation remains out of reach. Some researchers wonder if these constants are truly constant at all, or if they might drift slowly over billions of years. Current experiments suggest they don't. Light from distant galaxies behaves exactly like light in our labs, and gravity pulls the same way across the vast reaches of space. Yet the search continues, because even the smallest change would transform our entire understanding of reality. Recently, science has shifted toward defining our very units of measurement by these constants. We no longer just measure the speed of light, we use it to define what a meter is. In a sense, we have locked our system of weights and measures to these cosmic values. This makes the question of why they exist even harder to ask, as our rulers are now tied to the very things we are trying to investigate. These numbers point to something beneath the surface, a hidden logic or a necessity we haven't yet uncovered, but they leave their mark on every equation we write and every star we study. It is easy to assume that the laws of nature have always been there, but if the universe had a beginning, we must ask if the laws had one too. Did they exist before everything else, or did they emerge with the cosmos? The earliest moment we can speak of is the Big Bang, before which there was no space to expand and no time to move forward. Without time, the concept of before loses its meaning, making it difficult to ask if the laws were waiting in the void for the universe to arrive. Some believe the laws were born alongside space and time, packaged into the first moment like software loading when a computer starts. Others suggest the laws must have existed first in an abstract realm, acting as a blueprint for reality to follow. If the laws came after, what guided the universe in its first breath? Why did particles form, and why did space expand in just this way? There must have been something giving direction, yet without laws, how could there be any predictable behavior? Conversely, if laws existed before the universe, where were they? To exist outside of space and time is a concept that is almost impossible to grasp. Perhaps asking when the laws began is the wrong question, as time itself may be a product of those laws. Some models suggest that space and time are not fundamental but are built from something deeper. In that case, the laws aren't just built on top of time, they are the machinery that generates time itself. There is even the idea of a universe that bounces rather than bangs, where laws might carry over from one cycle to the next, slowly evolving and learning new behaviors over cosmic ages. We are constantly pushed back to the same boundary, what started it all and what guided the process. We cannot ignore the role of cause and effect, which serves as the skeleton of science. But causality requires time, there can be no cause without a before. If time began with the universe, then the universe might have no cause at all, it could be a spontaneous event governed only by the rules that define it. Quantum mechanics offers a glimpse of this, where particles appear and disappear out of nothingness. Some suggest the entire universe is a giant quantum fluctuation, but even a random event needs a framework. This brings us back to the laws. There is also the possibility that what we call laws are not the true foundation, but merely surface patterns we see from our limited perspective, much like a wave looks smooth from a distance but is made of countless moving molecules up close. The deeper layer might be a wild and shifting landscape, and our laws are just the average behavior of that chaos over vast spans of time. We know the visible universe has rhythm and balance, held together by something that shapes its path and limits its possibilities. But whether these rules are eternal, created, or evolving is a question that may lie far beyond the boundaries of science as we know it. Einstein showed us that space and time are two sides of a single structure, where the speed of light acts as an unbreakable boundary. Why can't anything move just a little bit faster if we give it enough energy? To understand this, we have to look at the relationship between motion and energy. As an object approaches this cosmic speed limit, the energy required to push it further doesn't just increase, it explodes. To reach that limit, any object with mass would require infinite energy, which is a physical impossibility. This limit applies not just to objects but to information itself. We cannot send a signal faster than light. This is why we see the stars as they were in the past, with light taking years or even eons to reach us. This speed is woven into the very fabric of cause and effect. If you could travel faster than light, you could send information back in time, breaking the order of events and shattering the logic of physics. This speed limit separates the possible from the impossible, keeping the universe predictable. It sets the pace for change and interaction, providing a natural delay that keeps everything from happening all at once. Finally, we find that symmetry lies at the heart of it all. In physics, symmetry means that something remains the same even when you change your perspective. Every deep symmetry in nature corresponds to something that is conserved: energy, momentum, and balance. These are not just rules imposed from the outside, they are the silent power of balance built into the universe itself. These symmetries determine the behavior of every field and every particle, forming the invisible foundation upon which all of reality is built. This is why modern physics treats symmetry as its ultimate compass. To understand a new force or predict a new particle, scientists look for the symmetries that might allow them to exist. This method has proven successful time and again, guiding the discovery of the building blocks of matter and the invisible fields that bind them. In a sense, symmetry tells scientists what is permitted and what is forbidden, which doors are open and which are bolted shut. But symmetry is not always perfect. In fact, many of the most interesting parts of our universe come from symmetry breaking. Imagine a pencil balanced perfectly on its tip. In theory, it could fall in any direction, a state of complete symmetry. But when it finally falls, it must choose one direction, and the symmetry is broken. The rules haven't changed, but the result no longer looks balanced. This kind of symmetry breaking is seen everywhere in nature. It is believed that in the extreme heat of the early universe, all forces were unified in a single, symmetrical system. As the universe cooled, these symmetries shattered, separating gravity, electromagnetism, and the nuclear forces into the distinct roles they play today. Even mass itself is thought to be a product of this breaking, born from a field that emerged when a certain symmetry collapsed in the early cosmos. Without this, particles would fly at the speed of light, unable to form atoms, stars, or life. Symmetry creates order, but it is the breaking of symmetry that creates diversity and texture, allowing simple rules to give rise to complex and varied results. Symmetry also has a startling connection to time. In our daily experience, time flows in one direction. We remember the past but not the future. Stars burn their fuel, and they never unburn. Yet the fundamental laws of physics are symmetrical in time, meaning they work the same way whether time moves forward or backward. The arrow of time we experience might not be built into the rules themselves, but rather in the way the universe unfolds and grows toward greater disorder. This suggests that the deepest structures of reality are indifferent to the direction of time, even if our lived experience is not. This realization pushes us toward the search for an ultimate symmetry, a grand structure that explains not just particles and forces, but why the laws themselves exist. Some dream of a final, perfect symmetry from which all of physics flows naturally. Until then, we are like people solving a vast puzzle, looking for the repeating patterns and balanced shapes that whisper of a hidden architecture behind everything. Some theories, like string theory, suggest that the laws we see are determined by how hidden dimensions are curled and shaped. This creates a landscape of countless potential universes, each with its own version of reality. In this view, the physics we know is just one option on a massive menu, a single bubble in a vast multiverse where other realms might follow entirely different scripts. The bridge between these symmetries and the laws we observe was revealed over a century ago by the mathematician Emmy Noether. Her work showed that every symmetry in nature corresponds to a conservation law. If the laws of physics do not change over time, then energy must be conserved. If they do not change based on your location in space, then momentum must be conserved. If they remain the same when you rotate your perspective, then angular momentum is kept in balance. This is why planets keep spinning and why skaters spin faster when they pull in their arms. Noether revealed a blueprint where the deep, unchanging patterns of the universe are the reason why certain things are never lost. Energy isn't just saved by chance, it is saved because time itself is symmetrical. This idea is the foundation of the standard model of particle physics, where forces and particles emerge almost automatically from the requirements of symmetry. It explains why an electron always has the same charge and why the universe maintains a silent, mathematical fairness. Even when we hear that a law of physics has been broken, it is often an illusion, a sign that we are simply seeing a more complex set of rules at play. Like a balloon that seems to defy gravity by floating upward, these events usually obey a more complete set of laws that we are just beginning to understand. We are constantly refining our map of these patterns, moving closer to the core symmetries that define the limits of the possible. In science, there are many cases where a rule appears to be broken only because we understand just a part of the system. Imagine a machine that seems to produce more energy than it consumes, appearing to violate the conservation of energy. But as soon as every input is carefully measured, the extra energy is explained not as a miracle, but as a misunderstanding of the whole. These false violations vanish once all the relevant factors are brought into the light. However, sometimes experiments truly push us into territory where our existing laws no longer work. This is the real challenge. It's not a misunderstanding, but a sign that we are missing something fundamental. When this happens, scientists don't immediately throw the laws away. Instead, they test and retest, striving to eliminate every possible error. Because established laws have survived countless trials, a perceived violation usually means the law needs to be expanded rather than discarded. For centuries, Newton's laws of motion worked perfectly. But when people began to measure motion at extreme speeds or near powerful gravity, the rules began to fail. Einstein's relativity didn't break Newton's work, it contained it as a special case. At low speeds and weak gravity, Einstein's equations give the same answers as Newton's, but near the speed of light or a black hole, the full theory is required. What we call a broken law is often just the edge of its reach, where a broader law is waiting to be discovered. Quantum mechanics is another example. Before its arrival, we thought particles moved in smooth orbits like planets. But in the quantum world, a particle cannot have both a precise position and a precise speed. This didn't destroy classical physics, it replaced it in a new domain. For cars and baseballs, the old rules remain true, but at the scale of an atom, the rules change. Nothing is broken, the laws simply shift as you zoom in. Sometimes, the breaking of a law is even more dramatic, as seen with conservation laws. In the early study of beta decay, energy appeared not to be conserved. A neutron turned into a proton and an electron, but the energy and momentum didn't add up. It seemed like a fundamental rule had been shattered. Yet, physicists made a bold guess, perhaps an unseen particle was being released, carrying away the missing energy. This particle had to be tiny, neutral, and nearly impossible to detect. Later, this particle was proven to exist and named the neutrino. The law was not broken, the mystery was simply hiding a missing member. We see this pattern again and again. The apparent failure of gravity to hold rotating galaxies together led to the idea of dark matter, an invisible substance that adds mass without emitting light. These apparent violations push us to expand our understanding of what the universe is made of. A truly total break in a law would be something that no amount of new knowledge could explain, a repeatable event that defies all logic and cannot fit into any broader theory. So far, that hasn't happened. Every apparent failure has ultimately proven that the problem lay not with the law, but with our understanding of the big picture. Scientists remain vigilant, using colliders to look for rare events and telescopes to watch for strange signals in the sky, hoping to find a real crack in the framework. Physics laws are not commandments handed down from above, they are models we build to match the world we see. Like any model, they can be refined and made more accurate. A true break doesn't mean the universe is falling into chaos, it means we have reached the limit of our current reach, which is usually the starting point for the next great leap. This is why scientists were so careful in the famous case where particles seemed to travel faster than light. After careful checking, the anomaly was traced back to a loose cable and a faulty connection. It wasn't the law that was broken, but the equipment. Yet, that moment showed how open science is to being wrong. If a result stands up to scrutiny, the rules are rewritten. It is not the end of physics, but the start of a new chapter. Our laws are both fragile and resilient, they rely on evidence rather than belief, and as long as every test aligns with them, they continue to lead the way.